So we're going to go ahead and take your time eating, get more if you want to. There's trash can in the back. But I'm going to go ahead and introduce our speakers and let them go ahead and get started because they have a lot of information to share. And our first speaker, a lot of you may know him. He's the Director of Forestry for the Village of Ruidoso, and he has about 35 years or more of experience in forestry. I'm sure he'll share a little bit of that information with you. That's Dick Cook right here in the green shirt. And then also speaking later is one of our citizen contributors, Mr. Leroy Cockrell, and he's a basically concerned citizen that's gotten very involved in his particular neighborhood, Black Forest, and is motivating his neighbors to take some of these things that Dick will be talking about and put them into practice. So I'm going to turn it over to these two gentlemen and sit back and take some notes.
Thank you. You know, we live in a pretty dangerous environment, and there's lots of things we do that can either help or hinder us in living in a safe community. And so what I want to do tonight is go through some of the fire behavior characteristics that helps you know what to do to protect your house. And so that's the reason our talk tonight is entitled Fire Behavior in the Wildland Fire Environment. Fire behavior and effect in the creation of a defensible space strategy. The objectives for tonight are to share information regarding Ruidoso's wildland fire challenges, understanding the wildland fire environment, factors influencing wildfire behavior, using wildfire behavior to develop a defensible space strategy for our own homes. The wildland fire problem is New Mexico has one of the most severe wildland fire problems in the world because of we have population, we have a lot of vegetation, and our topography is steep and rough and varied, and we have a climate that sometimes we're dry, sometimes we're wet, sometimes we're hot. And in wild and urban interface areas like Ruidoso, wildfire isn't a matter of if, it's a matter of when. And we've seen that in the last 3 years with the White Fire and the Little Bear Fire. Local conditions. In New Mexico, thousands of people choose to build homes within or near wildland areas. All these areas are covered with flammable vegetation. The environment may be desirable, but it comes with consequences. In mountain areas, forests with dense vegetation, steep canyons, strong winds, and high temperatures are really common. New Mexico's native plants and shrubs are among the most flammable in the world, most because of tree density and volatile oils within a lot of our plants and those kind of things, so they burn pretty hot. Local hillsides and canyons are covered with the flammable plant materials. The wildfire environment. We're going to talk about how a fire burns. When something burns, it's active combustion. We've all heard of combustion. Combustion is supported when fuel, heat, and oxygen get together in the right proportions. You get a flame or fire. Combustion then can be interrupted by removing the fuel, removing the oxygen, or removing the heat, or cooling the temperature. There are 3 ways a fire can spread. It can spread through conduction, which is when you build a fire and put something right next to it, it gets hot and burns. And so when it touches something, it can burn. Convection is also the way you cook. So if you have a barrier like a metal barn or something and the fire's close enough to it, it'll heat what's inside enough to make it combust. And most people don't know that solid fuels don't burn. They have to turn to gas before they can burn. So what we see in any fire is gas, it's not solid fuel. So the transfer of heat by contact, conduction, and radiation. Radiation is the heat you feel when you stand in front of your stove. You're not touching it, but it radiates with rays, heat out to where you can feel it. And then we have conduction, radiation, and convection. Convection is when you stand over a fire, and you're not touching the fire, but you have your hands over it, they get hot, so that's convection. Hot air, when it heats, rises, and that's what causes convection. Transfer of heat by contact, air, and direction is what most fires have in common. Here's a diagram that shows you a little bit about it. The wall represents the conducted heat. The convected heat is what's going up, and the radiant heat is what goes out. Now we've all seen, with Little Bear, we've seen the big plumes of smoke and the way they look. Well, this is what happens. You have a fire, the air is heated, the hot air is pushed up to the atmosphere into colder air, and when it gets up there, it starts to cool, and it forms the big clouds, which we call ice caps. When it does that, then the air starts dropping and coming back around, and then it starts to suck air back in, and so it's actually a circular motion that causes the big plumes of smoke that we see. There's what we call an ice cap. That's the hot air has gotten up into the area where it's cool enough, formed ice crystals, and formed a column like that. And that's also an example of convection. The gases are burning up there. There's no solid fuel involved, but it's being fueled because the trees and things are actually turning to gas, and that's what causes the big fires. This shows that when you burn a fire, that the tree is not in the convection column, so it'd be preheated by radiation. The branches, since it's in the convection column, would be preheated by convection and radiation. The bush would be preheated by radiation. The duff would be conduction and radiation, and the log would be conduction and radiation. And that just kind of gives you a little bit of an idea of when you start to get a fire, the way that happens. Now radiant heat transfer is increased. We're talking about radiant heat, and get something too close to radiant heat, it burns. And so when fuels are upslope from a fire, the flame, particularly if you've got wind, bends over closer to the ground, and the radiant heat actually burns the material out in front of it. Flames are bent by the wind, and flames are close to fuel, and when fuels are concentrated, radiant heat transfer is greatest. That's the reason if you have a big pile of logs, it gets hotter, and it does with the logs that are spread out. Some factors that influence ignition and fire spread are the fuels, the kind of fuels that you have there, whether they're pine needles or grass or bushes or just what it is. Fuel moisture is a factor that affects it a lot. Fuel size, fuel that are small, like pine needle branches, ignite quicker than logs. And so normally the smaller fuels are the fuels that actually carry a fire. They make it move. And then fuel continuity. Vertical spacing, which is little trees under bigger trees, and horizontal spacing. The vertical arrangement, they have three kinds of fires for that: the ground fire, surface fire, and aerial fire. Ground fuel are all combustible materials lying beneath the surface, including deep duff, roots, rotten berry logs, and other organic material. A lot of times it's called a peat fire. Sometimes we don't think that kind of stuff burns, but I was actually on fought fire in Minnesota, and we dig fire lines, and there'd actually be water standing in the fire lines, yet the peat on top had dried out, and it really created a pretty hot fire, and they're hard to put out. Surface fuels are those that are on the ground or just above the ground. Leaves, grass, down logs, stumps, large limbs, and low shrubs. And this is an example of a surface fuel. How fire spread? We talk about ladder fuel a lot. Fire will use a tightly spaced vegetation as a ladder to climb from the surface into aerial vegetation, like tree canopies. And usually does that through convectional heating. Convectional heating will start on the bottom and then go to the next layer, the next layer, the next layer. Convection, I got this picture because you can see that there's a lot of space between the bottom and the top, but the convection is actually taking the flame from the bottom and putting in those trees, in the top of those trees. And that's a good example of when you have a lot of ladder fuels, a lot of little pine trees, or a lot of brush, or those kind of things, it burns really hot. Aerial fuels are fuels that are above the ground. Tree tops, canopies, snags, moss on the top of trees, and bigger shrubs. Now, in the wild and urban interface, we have a number of burn enhancers that we have to deal with. Ammunition, most everybody has a gun or two, and that burns pretty good. Propane bottles, in some places we have natural gas, in a lot of places we have propane. Gasoline cans, does anybody have gasoline cans sitting around your place? Gunpowder, a lot of people reload, whatever it happens to have gunpowder in their house. Paint thinner, all those things are really explosive and really burn. And then in the wild and urban interface, we have concentrated fuel pellets we call houses. If you think about it, nearly everything in your house, the exterior of your house may not be, it may be metal or concrete block or whatever, but everything inside your house can produce a really hot fire. Now the horizontal continuity, that gives a fire an ability to move forward. This is a slide that shows you patchy. This fire won't get up and run very much because you've got spacing between the trees here. You also got good spacing between the trees. So this fire probably won't get up a good head of steam because there's too much distance between the big fuels there in order to move from one tree to another. So you may get individual trees burned, but you won't get a real roaring fire starting. Now this is uniform, this is sagebrush, and sagebrush goes hundreds of thousands of acres without a break in the canopy. And so up in the Great Basin, those are the kind of fires you have. And so you have uniform and continuous fuels over very large areas. And also, we have a lot of uniform, continuous heavy fuels in the mountains too. And that's one of the reasons Little Bear took off so, because we had a lot of continuous heavy fuels that were on the mountain when they came in. And so there's continuous fuel. Note there too that that's snow. Just because it snowed, we get the winds of 30, 40 mile an hour here. The pine needles will burn regardless whether there's snow on the ground or not. So we don't want to get complacent just because we got some snow on the ground. This is a picture I threw in here because it shows a fire down there, but it also shows tree spacing. And even though there's a fire that's burning down there, it's one that will probably stay on the ground. And when the fire stays on the ground, the firefighters can fight it. That's one that you just have to get out of the way. Categories of fuel: grass, leaves, and shrubs are light fuels. Limbs, logs, and stumps are heavy fuels, and whatever's in the middle is moderate fuel. If you look at those fuels, there's not much difference in size there. There's not a log. But the reason that light fuels catch fire easier is because there's more surface area to heat, and it lets off the gas quicker. And so that's the reason kindling starts better than the big logs you have in your fireplace. And so the bigger the fuel, the harder it is to ignite, but the longer it burns. There's light fuel. That's a grass. If you're standing by that fire, you might not think it was too light, but that's a good fire. But these grass fields that we have, like in our vacant lots and things, we have an ordinance that says you got to trim your vacant lot and around your house. But that's the reason, because the grass that's this high will produce a flame length that's about 2.5, 3 times the length of and those are gases that are coming up. So if you have even tall grass under trees, you can get the convection and get the trees started. This is a light fuel, and this is typically the way a lot of ponderosa pine needles burn. If they don't get into crowns, they stay on the ground, and when you hear them talk about prescribed fire, that's the kind of fire that they're trying to get, where it actually gets rid of some of the stuff that's laying on the ground, may kill some of the smaller trees, but it stays on the ground and burns pretty uniform and pretty consistent. There's a moderate fuel. It's not in the crowns yet, but there's enough heat there to where it generates a pretty good fire. These are what we'll call heavy force fuels. And if any of you went out towards Little Bear before the fire, we have a lot of what we call dog hair thickets. And that's where crowns overlap and you get a lot of flashy fuels. And that's what it looks like if it gets started. Small branches and needle ignite quicker and create intense heat. But there's less heat and volatility when individual trees ignite rather than when groups of trees ignite. And so there's a difference in term. In firefighting, a crown fire is one where it moves from crown to crown to crown. Torching is where 1 or 2 or 3 individual trees ignite. And when you get in a fire situation, torching is what you want if you have to have some fire. 3 fundamental parts of weather have a significant impact on wildfire. Temperature is a big factor. A few years back I fought a fire in Phoenix. The air temperature was 122 degrees. The fire actually killed 6 firefighters, and it doesn't take much to start a fire in 122 degree weather. Relative humidity is an important thing because the wetter vegetation is, the harder it is to ignite. And the wind. The temperature preheats fuels, and there's a couple, 3 kinds of preheating. There's radiant heat from the sun, and it'll hit the earth and will actually preheat the fuel before the fire starts. And so the warmer the day, the quicker the fire can get going because it's already a higher temperature before it starts. It preheats the ground. Affects air currents. And I don't know whether you've ever noticed or not, but in the mountains, as the sun heats up the ground, you get upslope currents. And so the air currents go up the hill, up the canyon. And then when it starts to cool off in the afternoon, air currents come downhill. And so that's a significant thing if you're talking about fire, because fire normally moves with the air currents. Reduces moisture in the air. The higher the temperature, the lower the relative humidity. Warm air can hold more water because the molecules of air are further apart when it's warm than they are when it's cold. And so even though there may be the same amount of moisture available, because it's warm air, there'll be less per unit of area than there will if it's colder. Now this is a little schematic that they're establishing what they call a trigger point, or an anchor point, where they actually start a fire line to fight a fire. And this particular fire, this is on a west-facing slope, or south-facing slope right there. And so that's going to heat up in the morning. And so that means that your upcurrent winds are going to carry that fire that way in the morning. And then as the fire goes over the hill, it's going to heat this slope. And so in the afternoon, you're going to get your upcurrent winds pretty strong over here, and you can tell by the smoke, the wind's going that way. And so what these firefighters are going to do is try to anchor on the lower end of it and flank it as it goes that way. So, but the thing that I want to relay to you are the heating of the ground causes the air currents that causes the fire to burn a lot the way that it burns. Relative humidity, water vapor in the air. Hot temperature reduces humidity. Cool temperatures increase humidity. Higher humidity, the higher the fuel moisture. And fires usually burn more rapidly during the day due to lower humidity. And in these wildfire situations, one time we were fighting fire up in the Pacific Northwest. It was in the sagebrush type. And the fire was making some pretty good runs. And our fire team got on it, and it got, at night, we were going to try to burn out so that we could put it against a road or something where we could handle it. And we tried everything. We had what they call a terra torch, which is essentially gel gasoline that we were trying to start it with. It wouldn't start. We tried helitorches, which is gel gas dropped from a helicopter. It wouldn't start. We tried fusees, we tried everything in the world. And the next day, the humidity dropped 2%. The temperature rose 3%, and fire was everywhere. And so it's pretty minuscule changes in the weather that can really affect fire behavior. The wind. The wind probably has the greatest influence on rate and direction of fire spread. Most of our larger fires that we have here in this area are kind of cigar-shaped. They're oval. They have a place where they start. Most of them go uphill and downwind, so they burn with the wind and uphill to get their start. And then after that, they can, as a matter of fact, the white fire, 10 miles in one burning period, and that was primarily due to a 40-mile-an-hour wind, and it stayed on that ridge pretty much. It stayed right with the wind and with the topography to burn a lot of country. It bends the flame closer to the fuel. It generally flows upslope during the day and flows downslope at night. It's variable and a lot of times unpredictable. And you can see the influence of wind. That wind, you can tell by the smoke, and that's burning upslope and downwind, and it's going to town. Here's, we talked a while ago with that diagram about the hot air going up, the convection column. If you look at this, this is a pretty good convection column to start here. If you look out here, you don't see much wind effect. But look at that little tree right there. Look at those trees. And when that convection column starts up, it gets enough oomph on it to create a vacuum where other air comes in behind it. And the air that's coming in behind it is what is actually bending those trees. If you look right there in that circle, you can see the effect of wind bending those flames in there. The same thing here. Wind's blowing this way, and you can see that it's actually a pretty flat country, but it's put that fire at a pretty good angle. And this is pretty good for seeing the effect of wind. That fire is pretty hot right there, it goes up, the wind hits it, and it goes that way. And by the way, we'll talk about it a little more later, but that's what causes your spot fires. The Little Bear fire was spotting about 2 miles out in front of itself. And that's the reason, that's because it had these big convectional columns there with a strong wind, and it pick up these embers and throw them out in front of it. This is a wind-aided grass fire, and you can just tell that that thing's just going lickety-split, and it burns out pretty quick. It's light fuel, but it'll really move a fire. Matter of fact, most of the firefighters that are killed on fires are killed in light fuels, not heavy fuels. And this is a heavy fuel. You can see the wind and things there too. This is kind of a neat thing that you don't think about too often. But if you go to a fire after the fire, there's a thing they call needle freeze. And you can just look at the needles that are remaining on the trees and tell which way the wind blew. Because the wind actually blows the needles and then they burn, and that's the way they stay. And in some of these fires, you go look at them and the needles going every which way, which means that it was really turbulent. Topography is the configuration of the land. It has a significant effect on rate and direction of speed. Matter of fact, wind and topography probably have the greatest impact, and they have much the same impact. 3 fundamental parts of topography are slope, aspect, and terrain. Slope, the steeper the slope, the faster the fire will move. The slope influences fire by preheating the fuels, and it's a convectional column that goes up in front of it that actually preheats the fuels. The gases and things actually preheat there, and by the time the fire gets there, it's ready to burn. Wind currents usually flow uphill, and that's during the burning period. And like I said, while the hot air rises, and so if you've got a fire, there's going to be some air going uphill. Convected heat causes a draft to bring in air behind it, and that's what creates the oxygen so that thing burns. And when you're fighting fire or around fire, you got to be careful, because when you're in steep country, stuff can roll down behind you and catch you. Parts of New Mexico, are any of you familiar with the Sotol? It's a desert plant out there, but when you fight fire on it, it burns off the base. Yet the top of it is still burning, and those things just roll like cannonballs down to the bottom and then come back up at you. This is just an example of a fire that was on a steep slope, and that's pretty typical the way it burned. It started down at the bottom and burned, got a little bit bigger as it went, and I don't know whether it went further in there or not, but it showed that little triangle shape. And slope affects fire behavior. Fresh air comes in behind it, it preheats in front of it, and the draft comes in behind it, the burning chunk roll down. Now this is a diagram that I put together, and when you got a wind coming from the left-hand side of that slide, you have the wind and the slope preheating that fire and moving it up there, so it's going to move up really fast up there. When it comes down this other slide, the fire, because convection wants to go up, the natural forces are fighting each other, so to speak, because the fire is trying to burn uphill, and so it's actually the conduction fire that keeps it going downhill. It's not a convectional fire usually when it backs down the hill, and so it usually burns slower coming downhill and out of the wind than it does going uphill with the wind. And here's a good example of that fire came over that hill, it's headed towards this town, and they'd done some fuel breaks and a few things up there, and so it's probably in pretty good shape because that fire is actually backing down there. It looks pretty bad. If you were standing in front of it, you'd probably want to run. But and there again, slope, shallow slopes tend to move slower than steeper slopes because you don't have the convectional heat out in front of it. It goes more up and not as much out. And there's an effect in these mountains particularly, they call it the box canyon effect or the chimney effect. And we actually had an example of that in the fire we had over across town 2 years ago.